Thank you, Federico, for your presentation. Welcome, everybody. Today I will present you our framework, which name is GRaCe. And it is a relaxed approach to graph caching, and it is oriented to give the results faster to user queries. And we start saying that nowadays it's a decade that we can see that the traditional web evolved in something we call web of data, in which we have a lot of heterogeneous and distributed sources. And we have also a semantic enrichment of our data, where the graph becomes the reference model of our dataset and also of our queries. What we can see is that databases becomes graph databases. Obviously, the databases is now defined according to the principles defined by RDF and also by linked data. And we have information that are represented as triples. So we can see here a graph in which Alice has an email like this one. This is a triple, so we have the connection between two nodes. Alice is the subject of our triple. Then we have email, which is the relation that links the two nodes, which is the predicate. And then we have her email, which is the object. Obviously, we have to have a language for querying such graph databases. The language is SPARQL, and so we can define the query as triple patterns. So we have the same structure for subject, predicate, and object, but we can use variables to query the database, and so to have the information. We can have multiple scenarios to have queries and to query the database. The first one is the one in which we have a linked open database in which we have multiple data sources spread into the web. And so we have the query, which is then parsed into a SPARQL query. The query has to be posted to a linked open data on the data sources in the web. And so we have something called source selection. So we have to select the right sources for retrieving the information for a given query. Once we have the sources for the query, we give these sources, we give the query and the triple storing the sources selected, we have to store in a local dataset. So we use this information, we combine this information to retrieve the result of the query. But also we can have something like this. We can have a SPARQL endpoint, which is an endpoint given by some of these sources. For example, DBpedia provides a SPARQL endpoint. So we have our query. The engine, the query processor, try to get the information about this query using an HTTP request. So it's given to the SPARQL endpoint, and we retrieve the results. The third and last scenario is the one in which we have a local dataset. So it's the traditional one. But obviously our dataset is always represented as triples. So our query processor try to get the result from the query and gives us the result. We have some issues related to these three scenarios. The first one, if we think about the first scenario in which we have to do, or also the second, in which we have to do an HTTP request, so we have to retrieve or the triples or the results, we may have an high response time. So the triples, the query takes too much time to get the result of the query. But if we think that we have multiple sources spread into the web, we may have offline sources, so we cannot get the right information. And this is a problem also for user satisfaction. We may have a result, but the user is not satisfied, okay? And so, this is a little sketch, but we have queries that we want to get a result as soon as possible. From this, we can try to give a possible solution. The solution is to use a cache that stores some information related to queries, and then the query processor, gets directly the results or the information associated with the queries from the cache, reducing a lot the query processing time. And so the caching can be defined as a system that stores information about previously executed queries, such as results or maybe also sources related to the queries, because in the source selection problem, when we get the sources on which we can put the query, okay, we can store also the sources to avoid some problem related to offline sources. But how is it possible to get the right query with the right information? We have to use some matching techniques that can be precise, so only the query that I'm looking for is selected, or also relaxed. So I'm trying to find also generalization or specialization of my query to get the results. The most common frameworks that has been presented nowadays are framework based on results. So we have results associated with previous executed query that use precise matching to get the query from the cache. And so only the cache items that precisely matches the query, the user request, are selected, and we have the results retrieved from the cache, so no processing is needed. But what happens when we have just similar cache items to the user request? The cache is not exploited, but it was the focus of our research. So our proposal is a smart caching framework, which is based on relaxed matching techniques, so we can select also not the same query, but a relaxation of the query that increases the number of possible matches with the cache. We can also use different kind of information associated with the query, so not only the result, but also, like I was telling you before, also the sources. And this approach is suitable for each of the scenarios I have presented to you before. So for a local dataset, we can use this method to select relaxed queries and provide efficiently the results of a query. But also for SPARQL endpoint, we know that we can store the triples in our dataset, and we can limit the number of connection to the SPARQL endpoint, but also for connection to the linked open data. So we have efficiently the results of the query. This is an overview of the framework GRaCe we propose. We have a query. The query goes to the dynamic programming planner that selects all the subgraphs inside the query, because we can have multiple subplans for resolving the query, like the traditional query processing. Then it provides a cache sheet if it is possible, so it performs a cache check inside the cache. Our cache is a table in which we store a label for each query, for each entry, and for each entry we have a tree. For each entry we have a pointer to the cached results, so we can derive the results directly from the cache. And once the dynamic programming planner has produced the plan, it gives to the engine that execute only the part of the query that has no match with the cache, and combine them with the cached results retrieved from the cache. Then it perform and join, and then gives you the final result. We started for this architecture from an architecture proposed by Papailiou in this article that I provide to you. So the goal is to perform this smart caching technique. So we base on relaxed matching, as I told you before, and we can see from this example that if we have this query and other queries inside the cache, for the exact matching technique, we cannot select any. No cache item is selected. But if we use relaxed matching, all these graphs inside the cache are possible hits for this user request. Yeah.
In terms of languages, what's the difference between SPARQL and say SQL?
I'm sorry?
What is the
SQL.
difference?
The difference is they are quite similar. They use only difference in the way we use the, for example, where condition. We have to specify the triple inside the where condition. So I have something like select the variable, and we can provide it from clause, like from a graph. We can tell from which graph, because we don't use tables, but we use graphs for posing the query. And then in the where condition we have something like subject, predicates, object, in which we have some variables that has to be bounded with the triples inside the dataset. So it changes like that. We can use filter condition like the SQL language.
So it's not an extension of SQL. Yeah?
It's not an extension. It's a language for querying graph databases. It's something else.
The
But
is different. So it's not based on relations, tables. It's for querying graphs.
Yeah, but couldn't, at least from what I saw there, it seems that a graph would be viewed as just a table with three columns.
Yeah. So it is derived from.
So your predicate, which plays a different role, so it's ad hoc.
No. The relaxed matching, just to end this part, is a way better than the exact matching, since we can have more cache hits. But the problem is that we get lower accuracy on query result, because you have to imagine that these queries are less selective than this one. Okay, so the cardinality of the result of this query is lower than this one or this one or this one. Okay, so we have more efficient processing, so we get faster the result, but we lose some accuracy on the results. The cache structure of our framework is something like that. Is a tree in which each node corresponds to a triple. The triple are represented, as I told you before, using a label. The label is a canonical label. I linked you to the article from Sigmod, because they explain well the canonical labeling. Each path of this tree represents a query. So if we read the tree from the root to the leaves, we have a query. And in each leaf, we have the cardinality of the result associated to the cache item. So we have more information associated to each cached query. In order to use the relaxation, we have to exploit some schema information about the resource we have inside the dataset. So we have to use something which are the RDFS subproperty of predicates, and also the RDFS subclass of predicate. These two predicates tell us that some property is a subproperty of another property, and the other one tell us that a class is subclass of something else. Okay, for this example, we have champion and champion in single, which are related with this subproperty of predicate, and also tennis and tennis tournament, which are related with the subclass of. This can tell us when a triple pattern relaxes or not another triple pattern. Okay, in this case, we have that, for example, the second triple pattern is a relaxation of the first one, since the predicate champion in single is relaxed by champion, which is more general inside the taxonomy, and tournament also is more general than tennis tournament. So we can use this query to generalize the first one. Okay? To select the best cache item, we have to deal with two selection. The first one is the selection of the best cache item. So we have to find a way to select the best cache item. And as I told you before, the second one is the selection of the best query plan, since we may have multiple query plan good for our query. For the first problem, if we have a cache, a user request, and the two taxonomy, the one on the predicates and the one on resources, we have to find the cache item that minimizes this function relaxC on Q and the cache item. So I compute something which is like a distance between the query and all the cache items, and then I select the cache item which has the minimum distance from the query, okay? Using, obviously, the two taxonomies as I told you before. Using this relaxC function, we can tell that if we compute the relaxC, the distance between the query and itself, it is the lower bound. And we know that the distance between the query and its generalization, it's higher than this value, okay? For selecting the best cache item, we use a modification of the A-star algorithm that allows us to find the best hit inside the cache tree. As regards the selection of the best query plan, we have to select among all the possible plans provided by the dynamic programming planner. For each subquery, we have a user request which is divided in subqueries. For each one is provided a query plan. So we have to combine different alternatives, and the alternatives are these three ones. So for each subquery, we may have that a query is resolved using an index, for example. We may have an index associated with our framework, or it is executed using the local dataset. For another subquery, we may have a precise cache hit, so we have the same subquery inside the cache. And for another, we may have a relaxed cache hit, so we have found for that subquery a relaxation, and we use that information. We can combine all the subplans using a cost function. We compute a cost function on the execution cost, so we assign an execution cost to the traditional execution of the query, to the precise and the relaxed, but also a cost of relaxation. So if we have the cost of relaxation for the two first cases will be 0, since we didn't have any relaxation here. But for the relaxed cache hit, we use the distance between the query and the selected cache item as a cost of relaxation. We combine this cost to find the optimal query plan. Yes?
When you say relaxation,
yes.
you expect that it will provide an over-approximation of the query, or could be both ways?
No, in our implementation is only a generalization of the query. So we have a superset of results of the query. Okay.
Because maybe it could be interesting to have also another approximation,
yes.
because if they don't differ too much, that gives you
we analyzed in the part related to source selection also specialization, which are something that we can take into account. But we think to focus only on generalization for this part, to have all the framework working for that part, and then to try also specialization, because it is.
And another question.
Yeah.
I would have expected that maybe there is not a best
query plan.
Best query in the cache
Yes.
that approximate the one you are interested in. So is that correct, or you always have a best?
Okay, we may not have any hit inside the cache, so we expect to get if there is at least one it for a query, we take the best one.
So there is always a linear order of among the relaxations. That's what you are claiming. Because if there is always a best one.
If there is at least one, yes, because we compute. So it works like that. If we check the cache for a query, okay? If we can get a set of possible matches for the query, we compute the cost, and then we take the one with the lowest cost. And this is the match. But if we cannot select any one of the query inside the cache, there is no match for the query. Okay, we can talk offline. Okay, thank you. Okay, I provide you some results of our experimental evaluation with a cache size of 50 items. We check for these three queries, and we can see that the execution time without using the cache, which is in the blue one, is the highest. Then using precise or relaxed matching techniques, we can have a speeding up for the query processing, so we can retrieve quickly the query results. But the problem is that using relaxation, we have that, for example, for the first query, executing the query on the dataset, we can retrieve only 12 results, but its best generalization has 37,000 results. So we have this lower accuracy that I was talking you before, okay? And also here you can see that there are 445,000 results instead of 74,000. Okay, so we have much more results that can lead to user the user may be not satisfied also. Okay, because there are more results than expected. Okay, what comes next? We thought that we can provide a cache replacement policy, since we have to select the items that can be stored inside the cache or not. And so we have to define suitable methods for replace some of these elements. And also we have to define a cache consistency. So we can base this consistency on some criteria. The first one can be a local criteria, which is we can quantify how many times a cache item is used, so using the frequency of the usage. But also we can define a global criteria, so how much cache items differs one another. Okay, so if we match all the items inside the cache, we can use a threshold to limit their distances, and so we can keep inside the cache only the queries that are above that distance, okay, above the threshold. So we may have different queries, not the same generalization, okay? Because the problem is that we may have inside the cache just one query that generalizes every other query, and we want to avoid that. Sorry. And the last part is the multi-level caching. So the thing is that we can combine two or more different caches. For example, the result cache that I present you today, but also a source cache in which we can store the sources of a query. And we can deal in this way with the dynamicity of the query, the sources, because we can say that we know that the sources are dynamical and changes their information a lot. And so we can combine these two to speed up also the processing and have also more precise results or more precise sources. And the question is, how can we combine these two caches, and I've done. Thank you.
Are there any questions?
Yeah.
Maybe you said on the missing
Mhm.
detail. When you retrieve the results
Yes.
obtained from the cache,
Mhm.
is there any way to sort your results according to how good you think they are, so associating some kind of confidence on the quality of your
Okay.
retrieved
Mm,
information?
okay. Right now, no. The answer is no. But we thought that some information about quality is also important for not only for the results, but also for the sources that we can select.
Mhm.
So yes, it is something that we could.
Because if they are many, maybe
Yes.
some kind of confidence may help the user in understanding which are the relevant ones.
Yes, but relaxation is something that the user knows that may happen. So the user is conscious that if it is okay for him to select also approximated queries,
Mhm.
he probably will get also relaxed results. So he knows that the set of results is bigger than the one for the. But it is true that using quality information we can in some sort filter some results.
Yeah.
Yes, but it is related to the query that the user poses to the system.
Thanks.
Yeah.
What are the factors that change how big is the set of relaxed results with respect to the original precise set? I mean, is it something like the more complex the query is, the biggest the set is, or is it about?
It is related first on the taxonomies. So since we have some information about the resources and the predicates and the way they are related one another, okay? So the generalization is given by the biggest is the tree, the more are the results that we can use as a relaxed results.
Okay, so the query itself is not that relevant?
No,
okay.
no, it's not query dependent.
So sorry, the relaxation is not query dependent?
No, the relaxation is query dependent, but the dimension of the set of relaxation is not dependent by the way.
I also have another question.
Yeah.
So, inside the cache, I can have many generalization of my query.
Yes.
And so to take the best one, the best one could be some kind of intersection of all the possible matches I found inside the query. So thinking order theoretically, the generalization is kind of an order between queries, and a generalized query is a kind of upper bound of your query. And so if you have to take the best one, usually you take the least upper bound, which could be the intersection of all.
It depends on the way you decide to store the relaxed query, because if you think about it, it was the problem I was telling you before. I may have in the cache the most general query of a one, okay, just one. But if I decide to keep in my cache a set of generalization of my query that differs one another of a threshold, okay, I can take I take the one that is which has the minimum distance between the queries. So I didn't take the smallest one, okay, because we talk about generalization. I don't know if I explained well, because it is something that maybe I
will get over it.
Yeah. Okay.
So thanks again, Francesco.
Thank you.
Just one quick word. This is the last seminar of this series. There is some break for the summer. We will start again pretty much at the same time as bachelor and master lessons, I think, in probably the beginning of October. I don't remember the exact date.
I think
So that's it. Thanks for coming.